In this video, let's use a line integral to solve for the mass of a slinky. So we have some linear density in grams per centimeter defined as the square root of x squared plus y squared. To solve for the mass, we simply need to integrate that density over the length of the slinky. So the contour here is going to be 4 cosine of t in the I hat direction, 4 sine of t in the j hat direction, and t over 4 in the k hat direction. Over here in the corner, I've highlighted exactly the curve that this traces. It's a nice slinky, and it goes from t equals 0 to t equals 8 pi. The first step to solving these types of problems is finding v of t. V of t is defined as the derivative of r of t with respect to t. So doing that, we take the derivative of the I hat component. 4 cosine of t has a derivative of negative 4 sine of t in the I hat direction, plus the derivative of 4 sine of t is 4 cosine of t in the j hat direction, plus the derivative of t over 4 in the k hat direction, which is 1/4 k hat. Sweet. So the next step for us here is to find the magnitude of v, which is done by taking the square root of all of the components squared. So negative 4 sine of t squared plus 4 cosine of t squared plus 1/4 squared. So this is equal to the square root of 16 sine squared of t plus 16 cosine squared of t plus 1 over 16. With these two terms, what I like to do is factor out a 16, and we have 16 times sine squared of t plus cosine squared of t. Now this is a trigonometric identity equal to 1, so we have the square root of 16 plus 1 over 16 is equal to the magnitude of v of t. So now that we have that handy, let's go ahead and substitute the values of the parameterization into our linear density function. And what I'm talking about there with the linear density function is this function in the integral. Anytime we see an x, we're going to replace it with the x component. Anytime we see a y, we'll replace it with the y component. So the square root of x squared plus y squared, when we turn it into t, becomes the square root of 4 cosine of t squared plus 4 sine of t squared. And following the same trick I did above here, where we get the where we factor out the 16, this just ends up being the square root of 16, which is equal to 4. So now we have everything we need. ds is equal to v of t dt, and our function is now in terms of t. So we have the integral over t, which we said ranges from 0 all the way up to 8 pi of 4 times the square root of 16 plus 1 over 16 dt. And if we evaluate this, we have 4t times root 16 plus 1 over 16. Evaluated for t goes from 0 up to 8 pi. Plugging in 8 pi in for t, we have 32 pi root 16 plus 1 over 16. And the units here are going to be grams because we integrated a linear density of grams per centimeter over the whole entire length in centimeters to get grams. So here's the weight of the slinky, and pretty much the slinky had a radius of 4 centimeters. So yeah, that's what we have for the weight of the slinky. Something I want to make note of here in this problem that's actually pretty cool is this term right here that we saw reduced down to a simple 4 once we parameterized it. So here, this term, it's root x squared plus y squared. Do you guys remember in cylindrical coordinates or polar coordinates that we said that r is equal to the square root of x squared plus y squared? Well, so essentially what we're saying is the linear density at a fixed radius is a constant. So pretty much along the entire circle, we have a constant linear density. So that's pretty interesting. I hope you enjoyed this video, and subscribe for more tips and tricks on how to solve problems and some practical examples.